Okay, this is David Zierler, director of the Caltech Heritage Project. It is Tuesday, December 20th, 2022. It is great to be back with Professor Ken Farley. Ken, thanks again for joining me.
Thank you.
Ken, today we're going to go all the way back to the beginning. I loved how you mentioned working with your dad to build a computer. Let's start with your parents. Tell me a little bit about where they're from, where they grew up.
Uh, Several different places, but mostly in New York City and Washington, D.C.
Which ones in which areas?
Mom in New York City and my dad in Washington, D.C. And they met in college at George Washington University.
And what were their professions when you were a kid?
My mom, for many years, worked as a technician in a biomedical lab. And my dad, early on, when I was young, he worked at UCLA as a physicist. And when I was about 7 or 8 years old, he took a job with Xerox as a principal scientist.
Did your dad have a PhD in physics?
Yeah.
What was his research area?
Yeah, this is a little bit funny. He worked in nuclear physics, and what he did for his PhD thesis was to determine the half-life of thorium-232, which interestingly is a quantity that I use all the time in my research, since that governs the rate of the production of helium-4 by alpha decay. So I've never cited his work because shortly after he finished his thesis and determined the half-life of thorium-232, somebody did it just a little bit better than he did, and got the number that goes in the big book of such quantities.
So growing up, you were definitely around science. You got exposed to academic science from an early age.
Yeah, I think there wasn't much doubt that both my brother and I would be scientists when we grew up. That was just so it seemed sort of obvious to both of us.
So your dad was at UCLA. Were you born in Los Angeles?
I was born in Santa Monica.
And you were there until you said age 7?
Yep.
And then where was the Xerox? Where was the relocation?
It was just outside of Rochester, New York.
Oh.
And interestingly, what my dad worked on when he was at UCLA, he was a soft money scientist, and he did a lot of work related to the Apollo program.
Oh, wow.
And in 1973, when the Apollo program suddenly vanished after being successful, it was not a great field to be a soft money scientist in. So he took a real job at Xerox.
And what did he do at Xerox?
I don't know. He didn't really talk about it very much, but I'm guessing it had something to do with the perfection of toner.
So he didn't talk about it not because this was like national security stuff. He just didn't share.
Yeah, no, I don't think it was. It was not something he brought home with him to discuss.
And did your mom have an educational background in science? Was that sort of her trajectory also?
Yes, she had a master's degree, I believe, in chemistry.
Did you recognize, or did it seem sort of path-breaking for your mom just generationally to work in science? Did that seem sort of ordinary to you or special?
It seemed fairly ordinary. She was a technician, and I think that was not that uncommon. At least I met several of her coworkers, and they were also women, so it didn't seem surprising to me.
And you grew up in Rochester through high school. You were in Rochester?
Yeah.
Did your parents or family ever note the weather differential moving from Los Angeles to upstate New York?
I don't remember my parents commenting on it, but boy, my brother and I sure liked the change. We loved going to a place with a lot of open space and snow and play in the woods, that kind of thing.
And you went to public schools, Rochester public schools?
Yeah, so interestingly, we were in a suburban town called Webster, and Webster is where Xerox had its big research and development facilities. So although it was out in the countryside, it was a lot of science and engineering folks in my high school, all of my schooling. It was a great place to go to school. I got a really good public education.
And for you, was it always going to be sort of more on the math and science track when you were thinking about colleges?
Yes, and I uh, was pretty on the fence between wanting to go into chemistry and wanting to do something like oceanography. And when I applied to go to college, the two places that I applied, one was Yale and the other was UCSD, which has a very strong oceanographic program, where I wound up going for my PhD.
Were there space programs or missions that you followed closely as a kid? Anything that might have planted a seed for what you would become interested in later on?
Uh, I can just say I do remember when the Viking landers landed on Mars, and I remember my dad came home from work and we watched the pictures show up on TV. You know, they kind of like scrolled across the screen. They filling the screen. The bit rate was so low. And I don't remember anything other than, wow, my dad came home to watch this. This must be important.
Why ultimately Yale? What was interesting there? What happened? What was happening there that attracted you?
I, I'm not really sure. I put a lot of thought into it. Um, the as I said, it came down between UCSD and Yale, and I obviously got into both. And I had been speaking with a chemistry professor at UCSD, and he said, "You'd be better off coming here as a grad student," and that made a lot of sense to me.
Why?
And
Because
so I have appreciated that I did go to a liberal arts college and picked up a lot of stuff that I would not have picked up along the way in any other way.
that was exactly my question. So UCSD would have been more of a technical education for your undergraduate.
Yeah, I guess I didn't go, so I don't know. But that was, looking back on it, the experience that I had at Yale was, there was a big element of things other than science and math.
Ken, how focused were your interests in chemistry right as a freshman? Did you have sort of a nuanced understanding of the kinds of chemistry you wanted to pursue?
No, not really. By that time, my brother was already in grad school at Harvard as a chemist, and so I knew pretty much what he was doing. And I hadn't actually thought about a specialization at all, and I had assumed that I would actually be doing pure chemistry. I didn't stumble on geochemistry until quite late.
And pure chemistry would mean what? Just sort of a more generalist approach?
No, as opposed to geochemistry.
I see. I see. Did you have any exposure to geochemistry or did you take geology courses as an undergraduate?
I didn't until my senior year, and in my senior year, I had started to see. Actually, I guess it was in my junior year that maybe I wanted to spend more time outdoors, and it was a good opportunity. I wound up in the summer of my junior year, summer after my junior year, when I was starting to work on the senior thesis project. I started out working in a chemistry lab, which I look back on, and it was in the sub basement, a windowless sub basement dungeon, and I did not really like that. And I wound up literally just talking to a professor I knew, a meteorology professor who I had met, whether there were any opportunities in that kind of field. And he wound up advising me to go and talk to a geochemist. And that person, that professor, his name is Carl Tarikian. He talked to me for about 5 minutes and said, I got to make some phone calls. I'll get back to you. And he made some phone calls to establish that I was not actually failing out. And he agreed to take me on as a summer intern. And so that's how I got pulled into geochemistry.
Ken, what were some of the experiments or laboratory experiences that were really formative for you as an undergraduate?
Well, after I started in that lab that summer, there was a research cruise going out of Hawaii that was being led by another professor, a UCSD professor, who then ultimately became my thesis advisor. And the person that I was working for, this guy Carl that I was working for, said, "Hey, you should go on that research cruise and get to know the chief scientist of that cruise. He's somebody that you might want to do your PhD with." So I had a very interesting trip in the summer I went on a research cruise that sailed out of Honolulu, and we did some water sampling. And we also landed on a handful of very tiny volcanic islands that are out to the north and west of basically of Kauai, places nobody ever goes because they're wildlife preserves, and collected rocks. And that was fabulous. I loved doing that. And that's kind of what I wound up doing for my thesis. So that was a great adventure. And after I got to know that professor, whose name was Harmon Craig, then in the spring of my senior year, he invited me to go on another cruise, which was amazing. This cruise started in Auckland, New Zealand, and went through probably 20 different islands in the Solomon Islands, in Papua New Guinea, places where it was extremely rare for anybody to show up. So we would sail up to these islands and get in a Zodiac and go ashore, and the people that lived there, they would come running down to the beach excited about literally seeing white people. So it was very fun, collecting volcanic rocks, and that some of the rocks that we collected on that trip became part of my thesis work. So that was a very good connection between what I was doing as an undergraduate, getting a chance to see what graduate school would be like, and also working with this very well-known geochemist named Harmon Craig. And so that kind of sold me on going to grad school at UCSD.
Did you stay sort of connected to UCSD throughout undergraduate, since you already had that point of contact at the beginning, and you had that option, come to us for graduate school? Did that sort of remain in your mind?
Partly. I don't think UCSD did. I did want to get to California. I liked California, and it just is a better fit for me. I spend a lot of time outdoors, and definitely in thinking about going to grad school at UCSD, I was thinking, yeah, there's a lot of great places to be outdoors in California. Not so much in Connecticut.
Was that where in California, when you went back for graduate school, that you got into ultra marathoning?
That actually started. Ultramarathoning didn't start until I was division chair, so that didn't start until many years later.
Oh, okay. Were you always athletic, though? Did you like to do sports and things like that?
I like to hike. I definitely like to go camping and hiking. I wasn't a particularly serious athlete.
So it was really from your senior year that you got focused on geochemistry?
Right. And so I wound up in grad school with very little background in geoscience at all. I'd taken one class in meteorology and one class that was very specialized but intriguing called Geochemical Methods in Archaeology. And I was quite fascinated by the fact that you could, for example, pick up a stone tool on, say, Easter Island, and you could establish that stone tool did not originate on Easter Island. It had been brought by the Polynesians from, somewhere very far away. And this is the way that it is well established that the Polynesians traveled from island to island. And anyway, I thought that was fascinating that the rocks tell you a story like that.
Now, I know UCSD is a relatively young school. Were the professors there sort of part of the founding generation of geochemistry?
Well, the people that I work with definitely were. They at that time, Scripps had a very strong program in isotope geochemistry, and including people that studied things like lunar rocks, and also in stable isotopes, which is the technique that gets used, for example, to determine climate histories, and also in noble gases.
Tell me about sort of the game plan when you got to San Diego. Who did you want to work with? What did you want to focus on?
Well, I arrived assuming I was going to work for this guy, Harmon Craig, who is a very famous, even at that time, he was a very famous geochemist. He had established a lot of the basics of stable isotope geochemistry. He had come from Harold Urey's lab. Harold Urey was the sort of founding physicist of a lot of isotope geochemistry, and he also Harold Urey was the advisor of just a whole collection of the greats in geochemistry. They kind of launched all at about the same time in the 1950s and 1960s. Harmon Craig, when I started, was a notoriously difficult individual. And I naively assumed that I could deal with it. And so I started in that lab, and I was, like most students, I wasn't really sure what I wanted to do, but unlike most students, I didn't really have very much background to understand why you would want to do some of the things that were being done. So I flailed around on various kinds of research projects that were not related to noble gases. There were other things that were going on in the lab that I worked on. But then ultimately, I wound up working on gases trapped in bubbles in crystals in volcanic rocks. And I really enjoyed working with the mass spectrometers. And that became my thesis.
Ken, do you see any value looking back in not having a strong background in geosciences at the beginning of graduate school and sort of needing to learn that stuff as a graduate student, not from your undergrad experience?
I'm not sure that I would say it was an advantage that I didn't know it, but I would say it is an advantage, or at least it felt to me like an advantage, to coming in being confident that I understood chemistry and physics pretty well. And, this is a relatively common situation when we admit students. They will come in with a similar background. And I encourage that. I think it is useful to come in with a strength that is other than in the field that you are ultimately working in. And in many ways, it is easier to come in with strength in chemistry and physics and learn geoscience than to have strength in geoscience and then be told, oh, by the way, you've got to go take an undergraduate chemistry class at Caltech. Taking an undergraduate chemistry class at Caltech can be quite daunting.
And you did that.
I didn't do it, but so I can get, when I started at UCSD, I had to catch up on geoscience classes, which are, they tend, there is a lot of qualitative material in geoscience and in oceanography. There's nothing wrong with that. Some people think it's, they kind of roll their eyes and think it's not real science, but boy, if you want to understand, for example, the way ocean circulation works, there is a very technical mathematical description of it. But then there is also just a lot of basic qualitative understanding that's important. And so that was I think it's easier to learn that than to go and actually try to learn all the really hardcore stuff. And also, by the way, be working on your thesis.
Ken, as sort of a prelude to developing your dissertation, as you got read up on geosciences generally and applied that to geochemistry, what were sort of the big questions in the field? What were the exciting projects potentially to work on, to make contributions to?
Well, in the lab that I was working in, the thing that attracted me the most was measurement of helium isotopes. So this goes way back in my career, partly because at that time there were literally only 2 or 3 places in the world where helium-3 could be measured routinely. It's a hard measurement to make. Requires a dedicated instrument. And at that time, there was they were kind of two broad things that were going on that are closely related, and I was interested in both. So I explained the last time that the helium-3 that comes out of the Earth is a vestige of the helium that the Earth accreted with 4.5 billion years ago. So there are 2 things you can do with this. One is you can learn about the geochemical evolution of the planet over 4.5 billion years. And it was pretty clear, even from the first analyses that were made on volcanic rocks, this is very surprising that any of that helium-3 had survived, because the general view was the entire planet had circulated through this giant convection system that brings the solid rock of the Earth's interior, it flows up to the surface, it melts, it erupts, it degasses, it subducts, and doing that for 4.5 billion years, running that big circulation system. It is surprising that any helium-3 survives. It is still surprising that any helium-3 survives.
Can you so the theoretical basis for why that's surprising? I wonder if you could just explain that a little bit.
Well, so it is important to understand that a lot of geoscience does not derive from, let's sit down and think about this and then go do an experiment. It starts with, let's analyze this rock and see what's in it. Oh my gosh, there's this helium-3 in here. Where could that possibly be coming from? And so here's actually how this works, because this follows the other pathway. I was going to tell you there are two pathways why helium-3 is interesting, or was interesting at that time. One is about the evolution of the Earth's interior. But the thing that was really motivating a lot of the work that was going on in the lab that I was working in at the time was very different. There was a set of experiments that were done in the probably 1969, something like that, that showed a very surprising thing. They were accidental. It was not the purpose of the observations, but Harmon Craig took a bunch of water samples from the ocean and discovered that there was more helium-3 in those samples than one could account for. And the way you would account for any helium-3 that was in there is there's a very tiny amount of helium-3 in Europe's atmosphere. That helium is in solubility equilibrium with the ocean. So the ocean has a little bit of helium-3 in it also. But what he showed is that at 2000, he had something like five samples, and there was one sample from 2,000 meters water depth where there was a little bit more helium-3 than you could account for. So it had a unusually high ratio of helium-3 to helium-4 compared to the atmosphere. And I don't actually know what his thought process was, but he made a most spectacular suggestion that this helium-3 was coming out of volcanoes on the seafloor. It was coming out of the Earth's interior at volcanoes on the seafloor. And that turned out to be the key thing that then drove a lot of exploration of where this helium-3 might be coming from. And in particular, it contributed to the discovery of hydrothermal vents on mid-ocean ridges. So you're probably familiar with black smokers. You get this 300 degrees centigrade water blasting out of the young volcanic rocks on the mid-ocean ridges. That's where the helium-3 is coming from. And shortly before I arrived in that lab, a postdoc working in that lab had made measurements very close in on the mid-ocean ridge, proving that that's where the helium-3 was coming from. Made a whole bunch of took a whole bunch of water samples at different depths across the ridge, and when you plotted it in contour, it looks exactly like a smokestack plume. That you can actually see the hot water coming out of the ridge, which has a very high amount of helium-3 in it. It comes up, it cools, it reaches neutral buoyancy, and then it blows along in the prevailing current. So that's cool. It establishes conclusively that the helium-3 is coming out of mid-ocean ridges, and it is actually a way to prospect for large hydrothermal vent fields. So this is a way that then others went on and found other hydrothermal vents simply by looking for these big plumes of basically the smoke that's coming off the helium-3 rich signal. But more importantly, this helium-3 is a tracer of deep ocean circulation. And that at that time and still today, the circulation in the deep ocean is very hard to characterize because it is extremely slow. So unlike the surface ocean, where you can put in a float and just watch where it goes on a 1 year time scale. If you put something in the Gulf Stream, you'll see that it travels 1,000 kilometers. If you put a neutrally buoyant drifter, and this is some of the work that we did when I was a graduate student on some of these cruises, we actually put something that floats at 4,000 meters water depth, floats neutrally, and there's a way to trace where it goes. And what you see is it moves really, really slowly, and it also is not. It's not like it's in a river. Instead, it winds up doing these very slow orbits. It moves one way for a while, then it moves another way. It's responding to things like tidal interactions. So it's very hard to use an active tracer like that. But the helium has been coming out of the ridge for probably forever. And so it has integrated over a long period of time. So this was of great interest to oceanographers who were seeing for the first time what the direction of the flow was. And there were some very surprising and unexpected features of that flow that were motivating a lot of the research cruises that I went on. So many of the research cruises that I went on did two different things at the same time. Collected water samples to map the distribution of the helium-3 blowing across the ocean or through the middle of the ocean. And as long as you were out there, you might as well stop at these volcanic islands and pick up some volcanic rocks and learn about the other thing, which is the composition of the Earth's interior. And I'm not sure exactly why I was more interested in the rock part of it, probably because it gave me an opportunity to spend time outdoors on volcanic islands in the Pacific. But that became my thesis work.
Ken,
so and again, going back to something I said before, the key thing for all of this is that there is so little helium-3 in the Earth's atmosphere that there's no that you can see these tiny. I mean, in the scheme of things, the injections of helium-3 into the mid-ocean ridge is tiny, but you can see it because there's so little helium-3 in the atmosphere.
Ken, I'm just trying to think if we can possibly connect the dots historically. So, of course, the Scripps Institution is one of the centers for the plate tectonic revolution in previous decades. Was there an infrastructure in San Diego that sort of had missions to the ocean, thinking about the mid-Atlantic ridge, thinking about that connected to the research that was available for you?
Yeah. So Scripps at that time and still today had a research fleet, and that research fleet was deeply involved in proving out plate tectonics, also in acquiring deep sea sediments and trying to unravel what is recorded in deep sea sediments in terms of things like climate change. So it's a big program that covers everything from physical oceanography, that is the mathematical description of fluid flow, all the way to sort of empirical observations of fluid flow, the type that I described. And then also, I historically, I don't know how it acquired this strong program in isotope geochemistry, but that was applied to all sorts of things, including lunar rocks, which have, of course, nothing to do with the ocean. So I think it's an example of when you start nucleating a strong group, it attracts other people with other interests because it's a hotbed of activity. And then you just go wherever your capabilities lead you. And that was, I would say, is probably where I'm certain that is where I picked up the technique-oriented approach to geochemistry, where if you've got an instrument that does X, you do everything you can with that instrument. And there were several different labs that were configured that way, that you could study the Earth's interior, you could study ocean circulation, you could study the moon. The relationship between them is all that they come back to the kind of measurement you make in the lab.
Ken, I wonder if you could explain just sort of data gathering for your thesis. What came from field work? What did you do that was, strictly laboratory oriented?
Most of my thesis work was on rocks collected from volcanic islands, and many of those volcanic islands were not amenable to any detailed fieldwork because they absolutely covered with jungle with no trails. And so many of the samples that we collected were literally cobbles on the beach, which in some ways is a no-no. You should never collect cobbles because you don't know where they came from, but is basically your only choice. And so there was not a big field component other than to collect those rocks. And as an example, one of the major parts of my thesis was studying two small islands off the coast of Chile called the Juan Fernandez Islands. And I was on a cruise. We collected rocks from there, maybe 60 or 70 samples, many of which were beach cobbles, some of which were in cliffs exposed at the beach level. Brought those back, and the analysis must be made on olivine crystals. So if you ever looked at a basalt, it's typically a gray rock and very often has these green crystals that, they can be up to 3 or 4 millimeters across. Those green crystals are olivine. It's also the gemstone peridot. Separated out, so crushed up the rocks, separated out those olivines, sometimes picking them with the tweezers, which is quite a painful way to collect a gram of material. With each one of those crystals is like a milligram, so you collect 1,000 of them with a pair of tweezers. And then ready to do the analysis, we crush up the olivine in vacuum. So we have a vacuum chamber, we crush it, and we purify the helium and introduce it into the mass spectrometer to separate mass 3 from mass 4 and to quantify them. This is exactly the same methodology that we use in my lab today. So it's a pretty standard approach to liberating gases from bubbles, which are in these olivine crystals.
Ken, returning to a topic from yesterday, the importance of instrument building, the importance of really understanding the machine, not just using what's off the shelf to do the science. Did you really develop that in graduate school, or does that really come from earlier, would you say?
I felt pretty comfortable developing capabilities in the lab when I was a grad student. But where I really picked up the thing which was, I think, most beneficial is after I finished my PhD, which is in itself a saga. I finished my PhD and I took a postdoc at Lamont Doherty Geological Observatory, which is part of Columbia University. And there I worked in a lab that was also primarily interested in oceanography, but they had they were very interested in automation. And I just thought that was spectacular because that completely resonated with my liking to play around with computers, and the very gratifying telling a computer. So much of my graduate work, I would have to, for example, come in both days of the weekend, turn a few valves, do a few little things. And then during the week, I likened myself to an automatic sprinkler controller. You turn this valve, you wait a little while, you turn another valve, and it doesn't make you feel great as a grad student if all you're doing is like looking at a stopwatch, turning a valve. When you could go to Home Depot and you could buy something that that did that. And then when I went to Lamont, they had figured out how to make the computer do all of that, which I loved. So that was the first thing I did after that. So I was a postdoc there, and then I came back California, got my job at Caltech, and implemented a lot of that. Spent a lot of time actually making sure that all of my lab could be as automated as possible.
Ken, to go back to developing the dissertation, the thesis, do you have a clear memory when you had a compelling argument or a finding this was going to be significant, what you were working on?
Yeah. There were really kind of 3 different directions that I was working on. The work on helium, I think it was useful. It was interesting. It was similar to what a lot of other people had found. But I also collected and was given additional samples from Samoa. And Samoa is an island chain, it's a volcanic island chain. And these rocks were very unusual, and they remain unusual to this day in that they were absolutely filled with bubbles. And that was really useful because to measure helium, you don't need many bubbles. To measure other noble gases, you need much, much more. And the reason for that is pretty simple. If you want to measure, say, neon, and if you thought helium was obscure, neon is even more obscure. But it tells a really interesting geochemical story. Unlike helium, the heavier noble gases, neon, argon, krypton, and xenon, are all gravitationally bound to the Earth, which means they are in relatively high abundance in the atmosphere. Why does that matter? It matters because if you are trying to see neon that is in a tiny bubble, you are surrounded by a sea of contamination of neon in the air, and it is very hard to get rid of it. Helium doesn't have that problem because helium is not gravitationally bound, so it doesn't have a high concentration in the atmosphere. Well, these Samoan samples had enormous concentrations, and we set off to measure the heavier noble gases in them. And those were really the first window for understanding what the neon and the xenon, those turned out to be the most interesting things that we got out of it, what the neon and the xenon looked like in the Earth's interior. And so that was the thing that when I gave a job talk at Caltech, that was the thing that people were most interested in.
Now, you mentioned finishing the dissertation was a bit of a saga. Was that related at all to your mentor's style?
Yes. Yeah. He was an extremely difficult person. And when I started, there were about 12 people in the research group. And we joked that we all got our ration of shit, but because there were 12 of us, the ration was pretty small. And by the time I was in my 5th year, it was just me. The whole group, for various reasons, had departed. And so it was very difficult. He was hypercritical and very controlling and did not like independence. And I was actually trying to collaborate with somebody external to UCSD, and he did not like that. And anyway, we had this huge blow up, and I literally said, "The hell with it! I don't care if I don't get a PhD. I'm not going to put up with this." And I walked out my 5th year. And I felt like I had been so obviously wronged that I thought that the administration would come to my rescue.
Did you go to the dean?
Yeah, went to the dean, and the dean basically said, you should finish your PhD with someone else. And whatever you produce, we will say is good enough. At that time, I had established a reputation as being a good student. I was not, people that knew that I was doing okay. The story turns out to be relevant. It's not just, complaining about the way I got treated as a grad student. So I did that. I went and worked in another lab and endured a lot of unpleasant interactions with Harmon Craig. And he, although initially he said, hey, you can't use any of the data you generated in my lab. You can't use any of that for your thesis. Ultimately, I don't know if somebody put the screws to him or what, but ultimately I was able to use it. But I was pretty discouraged. And this is a thing a story that I tell students who worry greatly about their personal relationships with their advisors and mentors. I was clearly in a very bad situation from that point of view and considered going to do something else. And I looked around for where I might be able to get a postdoc. So I basically finished my PhD. I did, while I was doing that in this other lab that I went to, I learned some additional useful new skills that served me well in the long run. But when I was looking for a postdoc, I applied to a postdoc at Lamont, and my reputation had preceded me. And a very well-known geochemist there named Wally Broker, who was famous for having done a lot of the first work to understand the way geochemistry records ocean circulation and how you could show that the ocean had circulated differently. So he's one of the first people that maybe even the first person that coined the phrase the ocean conveyor belt, which is key to understanding the way heat gets transported on Earth. Anyway, he had heard about me, and he asked me to call him when I applied. And he didn't do anything that was of direct relevance to what I was doing. But he said, anybody that is this much of a pain in the ass to Harmon Craig is okay with me. And he offered me a postdoc just because I was a pain in the ass to my advisor. And that set the rest of my, that was the step that I might not have been able to make, that I did make by just just my reputation.
Ken, being the last man standing out of the 12 graduate students until you had your own breaking point, what does that say about you? Is that just a higher threshold of pain? Were you not around because of all the field work? What might explain the fact that you were the last?
I was the youngest. I was not able to move on. It turned out, and it's not an excuse, but Harmon had cancer, and he was slowly winding it down, and he was an extremely difficult person, so I'm not going to excuse him for it. But I did learn a lot about how not to treat people. And there's sort of two ways you can go with this: the what you might call the abused child syndrome of, or you just say, I am never going to do that. And I definitely learned I am never going to do this in two ways. I'm not going to treat people that poorly, but also I am not going to make science the only thing in my life, because that's what it was when he was, in his closing years. He didn't have anything else. And it is very hard, and I will attest to this now that where I am right now and almost 60 years old, it is very hard to stay on the leading edge. And I'm not sure why it gets harder as you get older, but maybe it's because you have more other kinds of responsibilities you've got to deal with, or maybe it's just when you're 25 years old, you got a lot more energy or something. But you got to be okay with letting it go. And I watched both Harmon and actually several other well-known geochemists get to that stage and get bitter. Instead of saying, hey, I helped start all of this, it was more like, those people aren't giving me the credit I deserve for doing this or that. And it's unhealthy, super unhealthy. So it was a useful lesson for me. And then the other lesson I got from it is, people that are sort of mean and nasty, they probably don't want to be that way. It's not, they probably don't have any choice. It's just the way they are, which I think served me well over the years, to just deal with people that were being difficult.
Ken, maybe it's a philosophical question, but can you be a great academic scientist if you're such a jerk as a mentor? Are those things so intertwined that it's impossible to be one without the other?
You have to be a jerk, or you have to not be a jerk?
No. Is it possible, if you are a bench scientist and you don't have mentees, right? You can be antisocial and miserable and do great science. But for a professor who's charged with running a group and mentoring students and, shepherding them through the process and all of that, can you be considered a great scientist if the science is great but the mentorship is awful?
Unfortunately, yes. And there are plenty of examples of people who are unreasonably difficult. And I say that carefully, because there is a level of being difficult that is important. To be a scientist, you have to be tough, right? There's no choice. You have to be, because people are going to challenge your ideas. And if you wilt when somebody challenges your ideas, you're never going to succeed.
Yeah.
And you have to work hard, because there are other people who are going to work hard. And if you're not going to work hard, unless you are brilliant, which most people are not, you got to have something. And sometimes that's hard work. Sometimes it is just committing a huge amount of time. Those things are important. And an advisor has to basically say, you want to succeed, this is what you have to do.
Yeah.
And that's okay. If you don't want to play this game, you can get your PhD and you can go do something else. But if you want to be an academic scientist, this is what it takes. So there's a level of doing that. And then there's a level of, I definitely saw this when I got to Caltech. Another famous geochemist with a very similar background and a very similar personality, being a very difficult person, is Jerry Wasserberg. Probably even more famous than Harmon Craig. Extraordinarily difficult man. And when I arrived, so Caltech was the GPS division was in a very challenged position, it had a reputation for, especially in geochemistry, for having intense infighting between fiefdoms led by professors. And so I arrived, and I was the only untenured faculty member. So for the entire time I was an untenured faculty member, I was the only untenured faculty member in the GPS division. So I got tenure before we hired somebody else. So I was on my own figuring this out. And I actually think it served me really well when people like Wasserberg would come in and say nasty things to me. I would just shrug my shoulders because, I'd already learned how to deal with this. And by far, the way you deal with it, you don't gratify it. You just ignore it. If somebody wants to come and insult you, just, just go on about what you're doing. So unfortunately, you can be extremely difficult and get away with it if you are really good.
So maybe this is more of a generational question, but academic culture today, it at least strives to be more sensitive to the student experience, that there are more resources available when there are these challenges. So the behavior of your graduate mentor, were these the kinds of things that just wouldn't fly today? Or unfortunately, would they? Because they're not like, sexual harassment or racism or, the really overt red line stuff that absolutely wouldn't fly today. How would you understand that, if these were the kinds of things that you were coming up on, circa 2022?
I think a lot of them would be allowed to continue. I think there might be more attempts to steer people, away from doing that. But for better and for worse, a tenured faculty position, once you have tenure, if you are succeeding, it is very hard to redirect what a successful professor does. There are very few levers. Now, looking at it from the administrative point of view, there are very few levers to do that. Perhaps the only lever that is obvious is that when you write a research proposal, you have to explain how you are going to mentor students and how you have mentored students in the past. And I have yet to see that people that are difficult get penalized in review. If they come in with a great idea and a great track record for turning their ideas into important products, I think they still get rewarded. So I do worry about that. It's not a great situation, but there are definitely people who push very, very, very hard, and sometimes they produce fantastic students. And I have heard people say that this is necessary. This is the way you create the fantastic student, is you put them into a very difficult situation and you force them to perform so they learn how to do it.
Yeah, but difficult is not toxic. There is a difference.
Yeah, that's true. That's true. You can definitely go too far.
Ken, the road not taken, that dramatic moment when you thought, maybe you just leave the program altogether, not get your PhD. Do you have any idea what you might have pursued? Would you have left science also, maybe?
Probably not. I don't know what I would have done. What I was looking at the time was something like environmental consulting. I'm very glad I didn't go that route, but that would bring together in a similar sort of way the things I was interested in, which is outdoors, environmental stuff, and chemistry.
So the educational trajectory, Yale, San Diego, then postdoc at Lamont. Where is Caltech in all of this? Had you considered as an undergraduate, graduate, or postdoc? Did you think about Caltech? Did you consider? Did you visit? Were you aware of its reputation?
I didn't know a whole lot about it because the sort of direction that I was looking when I was a graduate student, the areas that I were most interested in were oceanic rocks, so islands in the ocean or rocks on the seafloor, and in terms of isotope geochemistry, the folks at Caltech, very well-known isotope geochemists, but they were not primarily focused on that. So there were people like Patterson, very interested in meteorites. He then also became very interested in lead contamination of the environment. So not something I was very close to. Lee Silver, super interested in the geochemistry of the continents. Same with Hugh Taylor. Wasserberg was interested in meteorites and the moon. So they were not really doing the things that I was paying attention to. And when I finished my PhD, by that time I was engaged, and my wife was also a graduate student at Scripps. She wasn't quite finished, but she moved with me to New York. And when we packed all our stuff up in my pickup truck, and we drove out of San Diego and then up I-15 through Cajon Pass. And as we were going up Cajon Pass, we both said, we are never coming back to Southern California. And I look back on that, and it's sort of ironic, but the reason I said that is one of the things that was amazing and very sad is when I started as a graduate student. I sound like a really old guy. When I started as a graduate student at UCSD in 1987, it was all of North County, San Diego was open land, and it was great. You could ride your mountain bike everywhere, and you could park near the beach. And by the time I finished my degree in 1991, it was all built out. It was like this sea of condos and traffic, and it was so overbuilt. And then the graduate students couldn't afford to live near the beach, and so we were having to move farther and farther east and commute. Anyway, I hated that, and it was just it just seemed like the Southern California thing to just sprawl everywhere. And so I said, we are never coming back to Southern California. And so this position I had at Lamont was a 5-year position. And I had been there only a few months when Ed Stolper called me and said, you should apply for our job. And I knew a little bit of Caltech's reputation at that point. And I talked to my advisor at Lamont, this guy, Wally Broker. And I said, I don't think I'm gonna apply. And he looked at me like I was an idiot. And he said, absolutely, you need to apply. You don't have to accept the job, but you need to apply.
You thought you were not ready for it?
No, so I did not want to go back to California, and I did not want to deal with any more assholes. And so this seemed like I was perfectly happy. I just started. My wife and I had actually just bought a house in Bergen County, New Jersey, and she was pregnant. So this did not seem like a great thing to just pick up and move, and I was not that keen on moving her again. But I decided, okay, I'll apply. And so I got invited out for an interview, and it was very memorable to me that it was in the middle of March, and New York in March is gray and muddy, and there's no leaves on the trees. and March in Los Angeles is beautiful. And everything was green, and Pasadena is not the creeping sprawl of a lot of Southern California. So I really liked it, and I got toured around, and yeah, Caltech was a pretty good, looked like a pretty good opportunity. I had a really good interview, and then I got offered the job and wound up taking it.
Ken, your explanation for, why Caltech wouldn't have been an option during your educational trajectory, emphasizing that it was really not part of oceanographic research. I wonder if you appreciated the history that Frank Press, for example, coming from MIT, tried to get the Seismo Lab, and that Caltech, in its Caltech way, said that's not our thing. We're not going to do that. Yeah. I wonder if you appreciated that self-consciousness to the kinds of things Caltech would get involved in and the ways that it wouldn't, and if that weighed on your decision making in terms of joining the faculty where you had all of these oceanic interests in mind, but maybe Caltech wasn't going to be as centrally involved in that as you may have needed it to be.
Well, right. So that, as I mentioned the last time, I was worried when I accepted the job that the only person that was working on things that were similar was Ed Stolper, and maybe a little bit Wasserberg, but I already knew I didn't want to have much to do with.
So his reputation preceded him. You knew about his personality.
Yes. Oh yes.
Because that was just known in the field.
Oh yes.
Yeah.
I have often pondered why the handful of really great isotope geochemists of that generation were all extremely difficult people, but they were, and so his reputation was well known. In any case, I think that the interesting thing that happened to me after I arrived is, I had started. I built my hammer. I built my lab. And was then looking around for what else could I do with it. And I already told you I got involved in looking at the cosmic dust on the seafloor, which originally was to get at this question of where this helium-3 coming out of volcanoes actually originated, but then turned into looking for major events in the history of the solar system. And then I also got involved in dating these apatite crystals to learn about the formation history of topography, so the formation of mountain ranges, working largely with Lee Silver. And those are things that I don't think I would have done had I not been exposed to the big diversity of things that happen that happen at Caltech. That are the difference really was a lot of the people that I work with at Scripps, they were completely focused on working in the ocean, and they didn't work on the continents. And that's why it didn't occur to me to work on the continents. But then I got to Caltech, and a lot of people working on the continents, a lot of interesting things happening on the continents.
Ken, when Ed Stolper first reached out to you, I don't know if you ever talked to him at the time or later on, how he became aware of your work. Was it really well cited at that point? Were you sort of giving a lot of talks? Would you have been known?
No. So I know a couple of things about it because Ed tells the story, and Ed is he remembers everything.
Yes, he does.
And what he told me was that, well, at the time when I got hired, I only had 2 publications, and I had not given a whole lot of talks. But Ed had I guess he was a grad student, either grad student or a postdoc named David Bell. And Ed struck up a conversation with him after an AGU meeting, American Geophysical Union meeting, and said, "David, did you see anybody interesting at the AGU meeting?" And David mentioned that he had seen me. And so Ed looked me up and decided that he should encourage me to apply. So it was purely because David Bell put in a good word for me.
So when you got there, tell me more about first of all, the job talk. What was asked of you? Because I know Caltech, when they're considering a new faculty hire, they want to see, is this going to be a faculty member who's going to make a massive impact on the field? Were you aware of that expectation? How did you respond to it?
Well, fortunately, I came in with a very low desire for the job. As I told you, it was, yeah, okay, I'll learn how to play the game. That would be my first real job interview, my first faculty position interview. And so I'll just learn how to do it. I was asked to give 2 talks, which I think is pretty standard, and that was straightforward for me to take the 2 chapters of my thesis that were most straightforward to explain and work through it. And I went and talked to each of the faculty members. I did not talk to Wasserberg because Wasserberg was on sabbatical, but I did talk to a whole bunch of other people, and it didn't feel like they were testing me. But I also felt like when we did so typically the way these things go, much more happens in the one-on-one conversations in people's offices than when you're given the job talk. And it definitely felt like they were wondering, okay, this guy knows how to measure noble gases, but what's it good for? And so this is sort of the corollary of, I was working at an oceanographic institution where people knew very well what you do with helium-3. I show up at Caltech where people are not doing that, and they're like, well, why would you want to do that? Maybe you should do something else. And so there was a fairly deep skepticism. And Ed has also told me that it was expressed very clearly, like, this is not a growth field. This is not a field that you can expect this person to work on for very long. So you better test them and see if they are interested in other things, so that when they run out of things to do with measuring helium, they can still do something useful. So I do remember that kind of conversation, like, well, what are you going to do for, in the long run? What do you want to do in the long run? And I think, like most people, I had no clue what I wanted to do in the long run. I didn't arrive with something that looked like a research program that could last more than a few years. But apparently that was not enough of a negative. I think, they must have discerned that I could at least hold my own for a few years, and after that, it is definitely the general structure of the way that division works and continues to work to this day is don't try to pin people down. Don't assume you know anything about what they're going to do. And this goes to the thing that I was saying yesterday, that you put people in an environment and give them opportunities and give them resources, and then you just watch where they go. You don't try to tell them where to go. They will go to wherever there is something that's interesting, if you've selected the right person. And that's definitely what it felt like for me. That I had a tool that would keep me going for a while, and then I just went off in all these different directions. I still happened to use the same tool, which was very convenient. So that's basically how that worked.
So just into a great postdoc, you buy a house, baby on the way. Why ultimately did you pull the trigger? Was part of the attraction the difficulty in going to Caltech and forging this on your own and having that, lack of certainty from the other faculty members? Was that sort of, in a way, attractive as a challenge to you?
There was a little bit of that. There was also something that was very obvious, that this was the big league. This is the job offer in terms of being able to start my own lab with very little postdoc experience. And being a postdoc is a scary time, especially when you're married and have a kid, because you got this responsibility to a family, and also thinking, this is the step. This is the really big step that you make, that you either stay in the field, and it sets where you're going to go in the long run. And I like the idea that, I could. This is as good as the offer was as good as offer as I was ever going to get, in terms of being able to start my own lab and so it just looked like it was the right opportunity. And by that time, I had also begun to see that Southern California wasn't so bad. The thing that was bad, that I did not like about it, is, and I think this probably remains unfortunately true, being a grad student, you don't get paid enough to not be kind of miserable. As a faculty member, you could at least have a hope of having a nice home and not having to commute long distances. And I feel very fortunate that I started at Caltech before it just became impossibly expensive. So I lived until about 10 years ago. I lived, it's probably 2/3 of a mile from campus, and I biked every day. I biked to work. You can't beat that. That was great.
You sold the house in New Jersey right away, or you hedged your bets? You hung on to it?
So I finished a year of that postdoc, partly to allow the lab to be renovated, which is an interesting story I'll tell you in a second, and also for the instrument that I needed to get. They're purpose built, and they're built on demand. So both of those things needed to be running in parallel with my finishing up the postdoc. So I stayed probably a year in total, so another 9 months after that, which meant my first son was born in Bergen County. So he's a New Jersey boy. And we drove across the country when he was 3 months old.
This amazing.
There's a kind of a funny story that the lab space that I was allocated was on the 3rd floor of North Mudd. It's not a lab anymore. It's now offices and a hallway. but at the time it was Claire Patterson's clean lab. And so you know Claire Patterson's story,
of course,
right?
Of course.
So his clean lab was his sanctuary, and it was the, as he would claim, the cleanest place in the world for lead. And he had an office right across from that lab. And so I show up, I'm walking around through the lab. So he had been, I guess he was retired, or at least not working in the lab anymore, but he was clearly not happy that I was taking over his lab space. And so he started out as, he was not a fan. He was not a fan of my coming. Ultimately, it was fine. But what was fascinating to me is there was a lot of barriers in that lab to keep the lab clean. But what was fascinating is when they pulled those barriers out, everything was rusted and falling apart, which is a very common problem, as I have come to understand, in clean labs, that there's a lot of acid vapor in those labs because you dissolve things like rocks. And the trick is to keep all that rust and stuff contained. But once they started pulling down the walls, just the walls were all falling apart, which is sort of odd. And I have two other interesting stories to say about Claire Patterson. He was a very unusual person. And he was in his, I don't remember when he died, but he was clearly withdrawing at that point. And I went to my first faculty meeting, which was probably 3 months after I arrived. I'm sitting around with the other faculty members in the Bewalder room, and we are in the middle of a planning exercise. These things you do every 5 or 10 years, where you go around the room and people talk about what area we should be studying. And so I'm sitting there. It was very interesting to listen to people say, oh, we should do this kind of seismology, or we should do this kind of geology. And then it came to Claire Patterson, and he stands up and he said, you have got it all wrong. We should be studying the human brain. And then he sat down. I'm like, what? He said we should study the human brain. And later, I went and asked Ed, like, what was that about? He said, that's just Patterson. That's just the way he is. He definitely thought we should all give up doing any kind of earth science and we should all study the human brain, which was quite weird. And the other thing that happened is while I was inspecting my lab as it was getting built, his office was right across the way, and I could hear him shouting into the telephone, I don't want your award. I don't want an award. And he had been offered some award for having the most highly cited paper ever in earth science, which is the Age of the Earth paper. And he was shouting that he didn't want an award for it. Like, okay, I get it. This is a very unusual person.
Now, when Dave Stevenson said this amazing thing to you about, just name your number, what was your response to that? Did you ask for more than you otherwise would have? Did that put more pressure on you to get it exactly right? How did you respond to, that open-ended invitation?
It was a huge relief, actually, because I understood what I wanted. And the hardest part by far is when you're trying to set up a lab is you can think of the big ticket items, but what is very hard to think of is all of the little things that if you are in an existing lab, they have, or they can borrow from somebody. And so I was having a hard time making the list of all of that stuff. And so to not have to worry about it, to basically just put in a number that would cover it was great. And I didn't change what I asked for. I asked for a single mass spectrometer and the components for a vacuum line. And back in those days, the big ticket items, you got co-funding from NSF. So I wrote an instrument proposal which ultimately got funded.
Whose space did you take over, or was it a new building?
So that space was Patterson's space. My new lab went into Patterson's space, and I stayed in there for, I don't know, 6 or 7 years. And then when the interesting thing that was happening at that time is all of geochemistry, there was a big collection of really important geochemists, and they were all retiring or dying. So Patterson retired, Wasserberg retired, Silver retired, um, Epstein retired, Taylor retired, and all of their space became available. And when we hired John Eiler, John was looking around for space, and he and I together, decided we should co-locate our labs as the two young geochemists. And so that's how we wound up in the basement of North Mud. Is let's just share a big space and take advantage of things that we will need together. And so, for example, like I bought all the tools, and so there's a giant tool rack down there, and if you need tools, it's all there. And it's more of an intellectual thing, actually, to always have people around. And that was very different than much of the way geochemistry worked in the fiefdom era, where it was sort of legendary that Jerry Wasserberg put a door in the hallway in front of his lab because he didn't even want people anywhere near his labs. And so if you could come in and work in Jerry's lab, you'd go through this door in the hallway, and then you'd never see anybody until quitting time. And then so you never had to interact with anybody who wasn't part of the lab group. And we were definitely trying to break that mold by having a big shared space, which now Alex Sessions is also part of.
Can this faculty response that, maybe your area of expertise will keep you busy for a few years, did you agree with that? Did you sort of defer to the graybeards, or did you say, no way, there's way more here than you're appreciating?
I didn't. I wasn't told that until probably about the time I got tenure. So I didn't have to know what people were saying. But I got pretty lucky, I think, in that the two new things that I worked on, which were this cosmic dust thing and the helium and apatite thing, they pretty clearly, within the first few months of working on them, I could see that they had a lot of opportunities in them. There were a lot of different directions to go, and for both of those fields, for many years, I had the field to myself. There was nobody that was geared up to do it for any number of reasons, but it was different than I think a lot of the way junior faculty get started. They come up with a good idea, they start something, to write a paper on it, and pretty soon other people are competing with them, and it's hard to build on it. I had the luxury of many years, and still today on the cosmic dust measurements, there are very few other people that can do it. And so I don't have to rush. I can lay out a plan and not worry that I'm going to get scooped on it.
Did you set up your lab in a way where new research opportunities would be easier to take on? Or, in the assistant professor years, is the idea you should be hyper-focused, you should make your mark in this particular area?
Yeah, that is a common question. Are you better off really nailing something or being diverse? And we always advise the junior faculty, you have got to do something great in one field. If you are just average in a whole bunch of fields, that's not going to be good enough. I don't know that I really thought about it, because one of the things I got told, probably by Dave and probably by Ed, just do your thing. Do not worry about tenure. It's not going to help. Just go do your thing. And if you need help, you need resources, you need advice, we are here for you. And that's, I think, is a really good piece of advice. If you try to game out, like, what is it going to take to get tenure, I don't think it's helpful. I did have a bit of a panic in that this purpose-built, this instrument that I got, it took a year for it to get manufactured. And the first thing that happened to it is, just before it was going to be shipped, something bad happened in the factory and they had to start again. And
oh, no.
They expedited it, but it still came about 6 months late. And I was freaking out, as a junior professor will do. The clock's running and I'm not doing anything. What I wound up doing in that time, I had all of these vacuum lines and the computers ready to go. And I spent 6 months writing code to automate the lines, automate the lab. And remarkably, we are still using a lot of the pieces of that code. And so it's something I never would have done. If I had had the instrument, I would have cobbled together some good enough code and then started analyzing samples, because that's how you make your mark. But it turned out to be quite beneficial to invest the time in the automation, which you harvest, the benefit you harvest for years and years and years after you do it. So if you're going to automate something, automate it at the beginning, not at the end.
So that's some serendipity, actually. It worked out
Yep.
that it was delayed.
Yep. Yeah.
So in terms of staying focused, what was the game plan? What was there to build on from both your thesis and what you had done at Lamont up to that point?
The thing that I continued to work on, which was the thing that was most obvious. I continued to work on these rocks from Samoa, made some additional measurements on them. But I think from the perspective that I just mentioned, where people thought, hey, you're going to run out of things to do, that is indeed exactly what happened, in that I couldn't see how to make the measurements any better. And I couldn't really see, because they were an unusual set of rocks that didn't provide any information about how you would find more such unusual rocks. They had lots of bubbles in them. It's not obvious how you would ever set out to find more of those. And so I think I came to my own realization that after a few years of doing this, I had done pretty much what I could usefully do. And so I was very glad to have these other two projects take off pretty quickly.
Which projects? What were these?
Looking at cosmic dust. So shortly after that is when I had that interaction with Don Anderson with Gene Shoemaker, and was off and running on that. And then for working on these apatite crystals, it was kind of an interesting interaction about that. So I was working with Lee, and Lee was a sort of a grand old man. Even at that time, he was a grand old man. He only died, I think, last year at some very old age. But he had this collection of mineral separates. And it's sort of surprising, but one of the biggest impediments to studying rocks is the need to separate out pure minerals from rocks that are in which they are in low abundance. So this mineral apatite, it's about 100 microns across, and it probably constitutes 1/10 of a weight percent of a granite. But you have to separate out that mineral if you want to work on it. Well, Lee had invested many years of his life doing those mineral separations. And so he had this room that was filled with little bottles of apatite grains and zircon grains and titanite grains, and they were just all up on his walls. And I sort of felt like I was humoring him when he was saying, wow, you could analyze these rocks. It didn't seem that interesting to me. But then I met the student who became my first graduate student, and details of this don't matter, but he was working on a problem that involved looking for fission tracks. Okay, so fission tracks it's a very unusual decay mode in uranium. So some very tiny fraction of the uraniums, instead of emitting alpha particles, they fission spontaneously, just like uranium-235 does in a nuclear reactor, except for it does it spontaneously. Well, the student was looking at apatite grains. He was working with Brian Wernicke, and he was looking at apatite grains that have these fission tracks in them, and he was using it to date the crystals. I'd never done any kind of dating at that point. So he was telling me, he was like, I walked by, and he introduced himself to me. His name was Richie Wolf, and he introduced himself to me and told me what he was doing. He says, I'm looking at these apatites and I'm counting the fission tracks to figure out how old this apatite is. And I'd never heard of this. And I went back to my office, and I had literally just been doing a calculation where I needed to know how many alpha particles, when uranium decays, how many alpha particles does it make compared to xenon atoms that it makes, or xenon isotopes that it makes? And the xenon is made by fission. So I just literally been doing this calculation about the ratio of alpha production to fission decay of uranium. So here's a student who's counting the fissions, and it pops into my head, wow, there's 10 orders of magnitude more alpha particles than there are fission tracks. So if he wants to date that by counting the fission tracks, he should just measure the helium. And this was my introduction to helium dating, which, as I told you before, had been proposed long ago, and it had never been made to work. And so I went back and I talked to Richie, and I said, Richie, maybe we should try to measure the helium in these. It's super easy to do this in my lab. So we went down and found Lee Silver, who had this trove of apatite crystals. And we said, hey, we want to see if we can date them. And Lee had a great idea. He said, let's go look at Mount San Jacinto. So if you know San Jacinto, it's a big mountain right outside of Palm Springs. It's where have you ever gone on the tram that goes up the side of Mount San Jacinto?
No.
It's fabulous. You ascend from, I don't know, probably just around sea level up to 9,000 feet. It's this sheer cliff made out of granite that Lee had sampled many years ago and had separated out apatite. And I didn't really know why Lee picked this place for us to do our first project on, but he did. And we dated those. So we measured the helium and the uranium, and it's easy enough to, if you know the decay rate, you know how fast the alpha particles are being produced, and you know how much is there, you get an age. And from 6 or 7 samples on this slope, this cliff on the side of Mount San Jacinto, it was obvious that there was something important going on, because there was if you plotted the samples against elevation, it was a perfectly straight line, with the oldest sample at the top being something like 60 million years, and the youngest sample at the bottom being something like 20 million years, perfectly straight line in between. Nature doesn't make straight lines if there isn't some basic phenomenon that's important, and that basic phenomenon is that mountain is being thrust upward, and the apatites that are at the top of the mountain cooled and started retaining helium before the ones at the base. And so you actually get information on when and how fast that mountain range was being produced. So it was a fabulous success right from the get-go. So Richie did his thesis on that. But there's an interesting thing that is just its commentary on the way the world works. I wrote a proposal to do that, to develop this method, which fortunately, I was very ignorant, totally ignorant actually, of the many fruitless attempts to use this method to date formation ages. So we're not getting at the formation age of those rocks. We are getting at the cooling history. Previous workers have been trying to get at the formation age, and it was disastrous. It was not useful because everything was too young. So I wrote a proposal to do this to the Geochemistry program at NSF, and it did not fare well in review. And I still have it around somewhere in my office. One of the reviews said, Farley is dumpster diving. I'm like, oh, that's not good. So it didn't get funded. But so I was kind of discouraged. And I ran into Brian Wernicke. And so Brian is a geologist. He just recently retired. But I told Brian what I was interested in. And he thought about it for a minute. And he said, I have a great idea. We are going to go and study the Sierra. And he wrote a proposal to a geology program at NSF and basically said, there's this new method. We don't know if it works, but it might answer this question that people have been interested in for 100 years. How long has the Sierra been a high-standing mountain range? And there's a lot of reasons why people have asked this question. I'll get to the answer in just a minute. But so he wrote this proposal, and instead of being reviewed by geochemists, who are all super skeptical of each other, it went to a bunch of geologists who said, well, I don't know if that can work, but if it can, it's really important. And it got funded. So we then embarked on this study of the Sierra, which involved a serious helicopter assault, all the way from the area around the Kern River. So in this very southernmost part of the Sierra, all the way up past Yosemite, stopping the helicopter going into wilderness areas and national parks. So a lot of permitting that was required to do this. But we analyzed those samples, and they basically showed the kind of pattern that Brian had predicted we would see if the Sierra were old. And basically, what we were able to show is that the two biggest canyons in the Sierra, which are Kings Canyon and the San Joaquin River Gorge, those are very deep, very wide canyons, and they have been there for at least 60 million years. And the only way you get a deep, wide canyon like that, you have to have a river that is cutting into the rock. And the only way a river can cut into rock is if it is high standing, right? You don't form a canyon below water, like underwater. So or under sediment. So that demonstrated what is now widely accepted, that the Sierra in the distant past, so 60 million years ago, were not necessarily a mountain range, but they would have been the leading edge of a high plateau that extended all the way from the Sierra to the Wasatch Mountains outside Salt Lake. This is a high plateau, much like the Altiplano in Peru, that has since collapsed. Anyway, it was a super interesting experience for me to collaborate with somebody who knew what to do with a method. And this is one of the things that I have really enjoyed that I mentioned yesterday, that it's fun messing around in the labs, thinking, like, can I do anything with this? And then discovering people that have good ideas, like Lee's idea to go look at Mount San Jacinto, and then Brian's idea to do it in the Sierra. And so you get brought along for the ride. And then for many years after that, I was collaborating with people from all over that had similar sorts of ideas for things to try. So that was great. That was a really fun experience.
Can the idea that, the concern maybe you would run out of stuff to do and the way that you initially set up your lab, did that influence your ability or willingness to take on graduate students where there's that 5-year commitment, you can keep them busy, we're not going to run out of problems to solve on? Or did branching out into these new fields sort of make those concerns go away?
The biggest stressor on a junior faculty member is the inevitable uncertainty of when funding is going to run out. And you absolutely cannot live your life that way. You just have to say something good will happen. And I definitely felt that. The biggest place where I saw it when I was trying to hire a lab tech or a lab manager, I can't commit to you because I only have funding for the next 2 years. Well, this is a real turnoff when you're trying to recruit somebody to tell them, like, well, you might have a job for only 2 years. And you just have to get good with assuming that it's going to work. And this is definitely advice that we give to junior faculty members. Do not worry about this. If you have a shortfall in funding, we are here for you. And I definitely got that. I didn't need it, but I got the reassurance. So I didn't really worry about that. I did not, and I have not have many graduate students. I have always worked with a small number of students. I think the total number of people who would identify themselves as my graduate students is probably 12 or 14 or something like that. So I have always run a relatively small group.
Can the older designation at Caltech, when you became associate professor in 1997, is that tenure? Is that what the associate professor meant at that point?
No. So I came up for the midterm review. You get an initial I think it's a 4-year contract. So you come up at the end of your 3rd year. And so I was promoted to associate professor without tenure, but then I got tenure the year after that.
Now, was that
So
standard? Like at Harvard, associate does not mean tenured. Is that how it was at Caltech
no,
also?
no, that was unusual even at that time. So it was just I'm not sure, it was some sort of practical reason why that happened. I don't know why it happened that way, but anyway, it came quickly, and so I got through the tenure period without in unusually short order, and partly, and this is just honest, this is something that is very hard to do when you have multiple junior professors because they are all competing with each other in some way. But as I said, I was the only one, and so there was no like, how is so and so going to feel if we give this guy tenure? So it doesn't happen very often, but it was a moment in time where it worked.
Now, where was John Eiler in all of this? Because you were, as you explained, you were sort of the two young guys at that point. Had he already gotten tenure?
No, so he didn't. He started probably right about then, right about 1997.
Oh, okay.
Something like that. He was a postdoc working mostly with Ed, and we were watching him, thinking, yeah, he'd probably be good for us to hire, and we let him search for jobs for a long time before we hired him, but it was a good hire. He's a great colleague.
Now, this vow that you asked Ed Stolper to make, that he was not going anywhere, what was the timing of that? Was that before you got tenure?
That was before I even accepted the job.
Oh, I see. When you did get tenure, did that open up sort of the kinds of things you'd be able to work on? Did that free up, those concerns about achieving great things in a specific area?
It didn't really change anything that I was doing because I think I did believe when I got told, don't worry about it. I mean, it was definitely for sure, a nice pat on the back. But I don't think it felt like, okay, now I can do other things. I don't think I changed what I was working on at all.
Was there a job talk for the tenure decision?
No. And it would be relatively unusual for that to happen, at least the way that we work.
So how was it communicated to you? Division chair, provost, how do you get the news?
I must have heard it from the division chair. I don't actually remember.
Clearly did not leave a mark, though. Not a big deal.
No, yeah, it was like I said, it was nice pat on the back. But
so at this point, by the late 1990s, where is JPL? Is it sort of already on your radar, or when does that happen for you?
I did not work at all with JPL until at least 10 years later.
Oh, wow. Okay.
And I remember, and I don't remember for what purpose, but I went up to JPL, and there's a really big difference between the feel of the Caltech campus and the feel at JPL, not the least of which is you can't even get on JPL without having a badge. And if you don't have a badge, you have to get escorted everywhere. And that is a challenge, and it's kind of off-putting. And so my first few experiences there were a bit off-putting. Like, yeah, I kind of like it where you can just wander around down the hallway and not worry about having a badge. And it's culturally, it's so strange that we're a single institution, and in one place we walk around and talk freely, and in another place there's a lot of locked doors and you can't get on the lab, and it's very different. It's culturally very different.
So to orient me, circa you achieved tenure the late 1990s, as we sort of did a tour of your research agenda where there's the mantle, there's the atmosphere, there's the seafloor. Had that been pretty much set at that point, that you were focused on these three areas, or what was not yet part of your agenda at that point?
Yeah, that's about right. That those were the main things I was interested in. I wound up at about that time. Actually, it was in 2000, because I remember that I took a sabbatical. I took my only sabbatical in 2000, and I went to University of Melbourne, and I met somebody there who became a collaborator that I still work with to this day, who is very interested in dating of iron oxide, and which is something that had not previously been datable. So iron oxide is, if you go to, especially to the tropics, and you see red soil, that red is all iron oxide, and it is it's a very insoluble phase. The reason you get those red soils is everything that can dissolve does dissolve, but the iron oxide stays. And so I started working with that. His name is Paulo Vasconcelos. I started working with him, and that then started a whole new sort of research direction where I got interested not in rocks that are deep-seated rocks that come to the Earth's surface, but what is actually happening at the Earth's surface. And that has two different components to it. One is the uranium-helium method. So the iron oxides accumulate uranium, or have uranium, and they accumulate helium. So we could date them. But the other thing, which we found along the way, more or less accidentally, is that those iron oxides also have helium-3 in them. You wonder, why would they have helium-3 in them? And the reason they have helium-3 in them is very clear, is when a rock is within about 1 meter of the surface of the Earth, it is subjected to irradiation by cosmic rays. So cosmic rays are high energy, at least at Earth's surface, they are high energy neutrons. That's not true in space, but at the Earth's surface, they are enormously energetic neutrons. And when those neutrons collide with target nuclei in a rock in the uppermost meter, they will shatter the nucleus that they interact with. And one of the particles they make is helium-3. So this has been known for a long time. Actually, it was discovered in the lab that I was in while I was there in about 1986. But what we discovered is that these iron oxides have helium-3 in them, and we use them to date how long they've been at the Earth's surface. And that led to what I think is one of the coolest things that we found, which people still scratch their heads at. Everywhere on the Earth's surface above sea level is either eroding or being sedimented in. It's just the way it works. If you are above the area of sedimentation, water flows across the surface and erodes. If you are below that region, you get sedimentation. Does that make sense?
Yeah, yeah.
So people have studied erosion rates using this production of isotopes by cosmic ray irradiation. And I hope it makes intuitive sense that a rock, here's the easy example that people use, and some of the work that we did unrelated to what I'm talking about right now. So a rock that is in a boulder in a moraine. Well, if you want to know when that moraine was produced, you can essentially translate into a question of, when did that rock first get exposed to cosmic rays? Because that rock was born somewhere deep in a mountain, and a glacier plucked it out and pushed it to the front, and then the glacier retreated and left those boulders there. So if you could determine the cosmic ray age, you can determine when that moraine was produced. Does that make sense?
Mm-hmm.
So I did some of that work. I had several postdocs working on that. Then I started working on these iron oxides, because that tells you about something different. That tells you about erosion rates. And people have looked in various places for where is the lowest erosion rate on Earth. And that's really not the way it's phrased, but as an ancillary thing, people have learned that had come to accept that the two most slowly eroding places on the entire Earth are the Atacama Desert, where there are places where it has never been recorded to rain, so it's hyper arid, or in the dry valleys in Antarctica, which is hyper arid and super cold, so there is no liquid water possible on the surface. It's frozen pretty much all the time. And we got involved in looking at the erosion rate of these iron oxides in Brazil. And we went to an iron mine in right on the boundary between Bolivia and Brazil. And it is this high standing plateau, sticks up 200 meters above the surrounding jungle. It's very weird. It's the Paraguay River Basin, this very prominent plateau. And we established that the erosion rate of this plateau is the lowest erosion rate anywhere in the world, much lower than the Atacama Desert, much lower than the dry valleys. And it's just because the way erosion works in those kind of environments is the rainwater falls and anything that can dissolve does dissolve, but the iron oxide is so insoluble, it just sits there, which was a really interesting discovery because then it explains why these plateaus are standing up. There's a whole bunch of these plateaus in the tropics. And this is the way they get produced. They get this cap of absolutely insoluble iron oxide on the surface. And then because the rainwater can't do anything to it, can't dissolve it, it just sits there. These turn out to be important because they're the major source of iron. The world's iron is mostly mined on these plateaus. So it's an interesting contrast. Anyhow, I did get involved in a completely different sort of direction that I continue to work on, which is learning about the geomorphic evolution of the Earth's surface using both cosmic ray irradiation and this technique for dating the formation of the iron oxides.
Ken, you mentioned computers, of course, were important from your lab at its inception. What were some of the computational advances circa late 1990s, early 2000s that might have allowed you to do either new things or the same things better?
So much of what I do does not require really high-end computation. So what I do is not driven by that at all. The thing that has been enabling for me is the ever increasing ease with which you can interface hardware to software. So being able to automate the lab in the early days, you had to know a lot about, you'd get a little terminal strip at the back with a bunch of wires, and you'd have to figure out, like, where do I put this wire, and how do I tell the computer to put a voltage on that wire? And all of that stuff has gotten super easy today. It's literally plug and play. You get the thing and you plug it in, and there you go. So that has made life a lot easier, but not a lot of computation really.
You mentioned you have to hope for the best in terms of funding. What were some of the big, around the time you got tenure shortly after, what were some of the big shots in the arm in terms of getting the support that you needed to do all of this work?
Yeah, absolutely. Packard Foundation Fellowship. These are spectacular. They are, I don't know if there's anything else like it.
Do you know if they have a long history with Caltech? They go back?
Yeah, so do you know about Packard Fellowships?
I've heard of it, but I don't know much, actually.
Yeah, so they're worth knowing about. So what they do is I can't remember how many they give out. It might be something like 40 a year. And there is a collection of they're called Packard Fellowships in Science and Engineering, or at least that's what they were called. I don't know what they're called anymore. They still have them for sure. But they interact with something like 40 major universities that do research, and they let those universities identify their top 2 candidates. So it isn't open to just everybody. There isn't an internal competition within those 40 institutions. And the pressure to nominate the best people, which you can imagine across all of science and engineering at Caltech, is very competitive. You have to be younger than 35, something like that, and less than 5 years after starting. So it's definitely a young person, junior person award. So they let the universities do the first order cut, and then I don't know exactly how they do the next one, but Caltech has in my memory has always gotten one of these, and so I got that in probably something like 1997. But the thing that's really great about these is they just give you a chunk of money. They don't ask for a detailed explanation of budget. You write a proposal, but it doesn't have to have all of the geez, writing a federal research proposal it's just all these things you have to have, and then you ask for a certain amount of money, and your reviewers say, well, that's too much, give them half as much. This is just a big chunk of money, and you can do whatever you want with it. And that's a level of trust that is very useful. And I think the year I got it, it was, even back then, it was $575,000, which was huge. No overhead on it, or some tiny amount of overhead on it. That is a big, big award. And so with that, I actually acquired a second mass spectrometer and sort of expanded my lab and supported more people. The biggest expense by far is people. In any lab operation, after you've gotten the initial, build the lab taken care of, it's the ongoing supporting of people that costs money. And to be able to say, yep, I've got money, it's in the bank, you come and work with me, that's great. It was really super helpful.
Do you know you remember the terms of the award, how much and for how long?
So for some reason, I think it's a 5-year award, and I think it was $575. But they're still doing it today. You could look up what they're doing, and they have a annual meeting at the Monterey Bay Aquarium, and so you meet the other fellows. And so I actually met a guy that was part of the class. So they call it a class. So the year I started, one of the members of that class about 6 years ago won the Nobel Prize. So it's a good collection of people.
Now, you built you added a second mass spectrometer. Was that so that you could do more of the same, or this was for new research?
It was within the same vein of what I was talking about, but it was a more modern, had additional precision, stability, took advantage of new electronics. So it wasn't fundamentally new, but I did keep both instruments going, and I actually kept my original instrument until about 3 years ago. So the original instrument that I acquired in 1994, I kept around until about 2017. It's kind of remarkable that it was still working. That's why everybody in the lab needed to know what a resistor and a capacitor were, because they had to get in there and fix it.
Now, you mentioned it was 10 years later when you really got involved with JPL. We'll talk about that in subsequent discussions, but I'm just curious, 1997, 1998, we have the proof of concept of a viable rover program on Mars. If you could just search your memory, did that register? Did you think maybe there's something there. Maybe there's real science that could be done on Mars?
Mm-mm. Nope. Did not register with me. But what did register was probably 4 or 5 years later. We'd have to go back and look exactly when it was. But there was the first talk about sample return. And that seemed interesting to me. I couldn't imagine that the things that I am most interested in, for which I have unique expertise, I couldn't imagine that those could be done with a rover. But I could imagine that samples that could be brought back would be very useful. And I think most people that do the kind of stuff that I do broadly defined would resonate with that statement, that bringing samples back, then we can all play the game. The early rovers, they have some analytical instruments, but they are not of the caliber. They don't have the same capabilities that laboratory instruments do. And many of us would say, bring a sample back, then you're talking. And I think in about 2003 was the first serious attempt that I'm aware of anyway, to develop sample return. And there were several different ideas about how sample return might be sample return from Mars, how that might actually be done. In hindsight, it's probably good that those things didn't fly, because they were what you might call grab and go. They were to just simply pick up a sample and bring it back. Whereas what we are doing now is much more like going into the field and searching for the right rock. And there's a kind of an interesting aside. It appears that the Chinese are going to attempt to beat the NASA-ESA collaboration to be the first to return a sample from Mars, but they're going to do it by grab and go. If they do it, they are literally just going to land, scoop up some dirt, and fly it back. And anyway, that's what was being talked about in around 2003. Even that would be pretty exciting to actually have something that you knew exactly where it came from. And also, probably about that same time was a realization that there are meteorites that originated from Mars in the collection. This is something that Ed Stolper contributed to. I think that was probably discovered sometime in the late 90s, or at least definitively understood that there are rocks in the collection that have come to Earth from Mars. And so that's, if you're going to do grab and go, why don't you let nature do grab and go? And so it's kind of good that thing never came to fruition. But that was the first time I remember thinking about it. And then by the time I became division chair, and we were trying to figure out how to allocate the Moore Foundation money. And you remember Gordon Moore, I can't remember what the number was. It's some extraordinary amount of money.
600 million.
Yeah, giant amount of money. And we actually built in the sub-basement of ARMS, we built a facility that has several ion microprobes, which are really high-end instruments for analyzing many different things on very tiny samples. We built that in preparation for sample return. Now, of course, sample return did not happen at that time, but it puts us in a good position for samples that come back hopefully 10 years from now.
Ken, you were director of the Tectonic Observatory for a year. I haven't heard of it. What is the Tectonic Observatory, and is that a short-lived directorship for you?
Yeah. So that was an interesting, I learned a little bit about the way the world works for that. So that was one of the two things, I think it was only two things that the GPS division had supported from the Moore Foundation funds. There was this facility that I just mentioned in the sub-basement of ARMS, which I was very intellectually close to. And then there was the Tectonics Observatory. So the Tectonics Observatory was an attempt to bring together geophysics and seismology, geology, and especially the kind of geology called tectonics, and geochemistry and geochronology, which is how I came to that. And this was a big chunk of money. I don't remember what the budget for the Tectonics Observatory was, but it was a lot for this group of people that, this group of faculty that identified. And then there was a bit of round and round about who should be the director and what should the director do. Should the director actually direct, meaning, okay, I'm making the decision, here's what we're going to do? Or was the director simply going to be the person with the sharp knife that cut up the pie and, you get your piece and you get your piece? And it was a very contentious experience watching this play out, because it was kind of a power struggle. And when it came time to decide who was going to be the director, I guess it must have been Ed Stolper, went and talked to all of the people that were part of it. And I was everybody's second choice. I was nobody's first choice, but I was everybody's second choice.
Wouldn't it have made more sense for a Seismolab person to run it?
It certainly would have made more sense for it to be somebody that was more front and center in that field. I mean, I was kind of peripheral to it. This is when I was doing a lot of the work that I was telling you about, looking at the uplift history of mountain ranges. And so I was working with Kerry C., who was part of this, with Brian Wernicke, a whole bunch of people, Jean-Philippe Abouac. So I was working with them, and they sort of knew me. And so I got asked to do it mostly to just get it going and try to ease the creation. And I did one of the things that I learned it's really bad when you offer something great like this giant chunk of money and it makes people unhappy. And that's what this was starting to do. Like, you offer up this thing that should make everybody happy, but they're not happy. And I took that to heart. Like, if you're going to offer up resources, then it needs to be in a way that does not create unhappiness. It's sort of not a great thing about human nature that people feel that way. But anyway, so I started in that position. I don't know that I would have succeeded in that position because I did not have a vision for what it should be. And I think that's why I was everybody's second choice. It's like, oh yeah, we'll tell them what the vision should be. I can be reasonably independent, and I can be reasonably penetrating when people propose what they want to do, even if it's not in my field. This is what I was telling you about, where I feel like, because I'm technique oriented, I actually have the ability to follow along in a lot of different fields. Anyway, I started in that position, and that must have been in
2003.
2003, yeah. But then I got asked to be division chair, and so I stepped back from that.
So for the last part of our talk today, as prelude to when you were named division chair, were you closely paying attention to Ed Stolper's style as division chair? Did you have a sense that you were like next in line and you should pay attention to what he was doing?
That became obvious to me probably 2 years before he finished. He finished his 10 years, which is at least traditionally the longest time you ever do it for. And I was an obvious candidate, and it is something that many people cringe when I say it, but it was a challenge that I thought would be interesting, and I would not want to say I wanted the job, but I was perfectly happy to take the job when it was offered to me. And I say that only because, for some reason, if you say that you think you could do a good job and you would find it interesting, then people look askance at you like there's something wrong with you. Like maybe you aren't a serious scientist or something like that. But in any case, I was paying attention, and I did admire a lot of the way Ed ran the division. I think he was very good at obtaining resources for the division, and he was also very good at breaking up some of the really bad behavior of the fiefdom era. I actually watched some of what were very hard conversations with some difficult faculty members, and because of my own experience, I'm like, yes, you can't behave that way. You cannot let people behave that way. And so he got in there and basically told them they couldn't do it. He told one professor who decided that thou shalt not smoke in, and this is sort of amazing, like in the old days you could smoke in these buildings, but there was a faculty member who thought the rule did not apply to him, and there was a battle, and the chairman won. So yeah, it was good to see his style. I did like his style, and I was learning from him.
Now, on the concept of fiefdoms, what about the Seismolab? That's not a fiefdom as a professor, but institutionally, I mean, one of the stories when it was brought in from the mansion, from the San Rafael Hills, was that it was something of a fiefdom off of campus, and that as an impetus to bring it into the fold of GPS, it really needed to be relocated to South Mud. Was the Seismolab considered a fiefdom in a different way than the professors?
There were definitely people that perceived it that way. Because there was a unclear way that you could be made a member of the Seismolab, and that caused some frustration. For example, with Carrie C, who he's a paleoseismologist. Should he be in the Seismolab? Should he not be? Should he be allowed? Should be given space over there? I personally didn't really see it that way because it didn't threaten me in any way. It didn't threaten my existence in any way, and I very much admired some of the things that at that time they were able to do, and I suspect they are still able to do, which is to have a collection of students who move very freely between different faculty members for doing their thesis work. So they managed to collectively guide their students, and that's very enriching if you can do, one project with one professor that logically leads you not to another project with the same professor, but to like, oh, well, this other guy knows how to do this thing that was the answer to the question that I just raised with this first project. And so they do a really good job at that. And I think it makes the students very broad in what they're doing. And if you look at where most of the faculty that we hired, many of them came through as graduate students. In a sense, it's a little bit incestuous, but it is a remarkably successful program.
Now, when the decision comes, is it as simple as the current division chair names his or her successor, or is there a more formalized nominating process?
The typical way that it works is that about a year before the transition, the acting division chair solicits input. Who are the logical candidates? And sometimes there are meetings. For example, there were meetings that I was not invited to because it was clear I was a candidate. So the faculty met, and then they provided input to the provost. So maybe the provost actually tasks somebody to report, like, who are the candidates and what are their strengths. And then I think that individual who's ever tasked to do it makes a recommendation, and then it goes through the administrative part of it.
Ken, last question for today, and we'll build on this in our next. In the way that you admired Ed's leadership, what he had done for GPS, when you decided to take this on, what aspects of the division chair for you did you see as caretaking, that GPS was in good shape and it was your responsibility to continue in that trajectory? And where were there obvious areas for improvement that you would be able to take on?
There was definitely an element of division's in great shape, don't you dare break it. And there was a visiting committee that might have even said something like that. Like, division's in pretty good shape, and the key goal is not to break it. And I, just like with the Tectonics Observatory, I did not start with a vision of what we should be, other than we should be the group of people that we are. I mean, I wanted to do the job. Like I said, I'm a little reluctant to say that, but I was willing to do the job because I totally believed in this group of people. And I would not say most of them were my friends. They were my colleagues. But I knew that the vast majority of them were really excellent scientists. And I felt like I could do something to facilitate what they wanted to do. And so this was because there was a lot of money coming in from the Moore Foundation. I mean, we were in good shape financially. So I did not have to deal with any sort of big problems other than the inevitable need to keep replacing people. And when we in the GPS division go to hire somebody, it's not like when, let's say, engineering wants to hire a mechanical engineer and they put an ad out and they get 250 candidates, and surely one of them is going to be good enough. It doesn't really work like that. If you put an ad out for a seismologist in any one year, you may not find anybody you like. So it's an undertaking, and it requires a lot of patience. And sometimes you go years without actually hiring anybody. And that was the situation in geochemistry, that when I got hired, they had gone, I don't know, they were doing a search for 5 years before I got hired. And so there is the need to continually rejuvenate the faculty, even though most people in the GPS division, or at least many of them, spend their entire career, as I expect I will. No reason to go anywhere else. So there's not much turnover. But even the turnover that there is with people spending, 35 years there, you still have to replace people. And so that was an area that seemed obvious to me that there would need to be attention.
Ken, on that note, we'll pick up in 2004. We'll see what happens next.